Mr. G with another video for the grade 12 related to acid and bases. This time we're going to be talking about dissociation constant, in other words the Ka and the Kb. But before we do that, please subscribe for the channel so you can get all the notification and videos I post on regular basis. Let's begin by defining what is a dissociation constant. And like we did in equilibrium, the dissociation constant is going to be K, and it's going to be the ratio of the concentration of product by the concentration of reactant. This one here is concentration of product. So it's the concentration of product divided by the concentration of the reactant. And now this dissociation constant that we're going to call K, which is this one there, that K, for the acid is going to be called Ka. So Ka is the dissociation constant for acid. That is all. It's just A for acid here. Well, if the Ka is high, it means that the acid isn't strong acid. The acid ionized almost completely. What is the meaning? That is the meaning of the high Ka. So for instance, let's see one example. When hydrochloric acid ionized in water is going to form hydronium ion H3O plus, and is going to form chlorine ions. Alright, now in this case, because it's a strong acid, this equilibrium is going to shift it to the right. In other words, it's going to be more of the product than reactants. This is what is going to happen. So if you calculate the Ka for this acid here, you will have that Ka is equal to the concentration of the product. In this case will be concentration of H3O plus multiplied by the concentration of Cl minus divided by the concentration of HCl. Water is not included because it's a liquid. So this is how to calculate the Ka. Because it's a strong acid, it means that the equilibrium is going to be shifted to the right. So it's going to be ionized almost completely. That is the Ka. If the Ka is low, we say that if the Ka is low, the acid is a weak acid. You must learn that, okay? So what does it mean? The acid ionized incomplete to form a low concentration of H3O plus. So if you have another reaction, another example, for instance, this reaction, now what is going to happen is that the equilibrium is going to be shifted to the left. That is what is going to happen here. And the concentration of the H3O plus aqueous here is going to be quite small. It's going to be much smaller than the concentration of the reactants. So that is what is actually happening here. So if we calculate the Ka here, in this case, it's still going to be the concentration of the product. So it's going to be concentration of H3O plus multiplied by the concentration of HCH3COO minus divided by the concentration of CH3COOH, because it's an aqueous solution there. That is what we are going to get. But the Ka, this one here, this Ka here is going to be low. It means this is weak acid. This one is a weak acid. Now the good news is we don't have to do these calculations, or I don't think you will have to do this calculation here. This here is high. It means this is a strong acid. We don't have to do this calculation. We have to be able to know that if this is low value, it means that the acid is a weak acid. That is what you need to know here. You need to know that this one here If this one here, the Ka is high, then it's going to be a strong acid. That's all you need to know from this side. Now, guys, we have to do the same with bases. We'll have for bases now we have the Kb for bases. And for bases is exactly the same, but the symbol is Kb. So everything else we did is the same. For instance, strong base will have high Kb. That's all we have to know here. And let's see one example. If we have a sodium hydroxide, sodium OH in aqueous solution, it's a solution plus water, will dissociate in water. Now this one, the equilibrium will be shifted to the right because the sodium hydroxide is going to be strong base. Therefore, this one will form ions of Na plus aqueous plus OH minus aqueous. All that will be in water. The equilibrium is shifted to the right. It means that the Ka here is going to be high Ka. This one is equal to the concentration of Na plus multiplied by the concentration of OH divided by the concentration of NaOH. Here we need to know that this Ka is high, which means that this one is a strong base there. Alright, so that is one example of a strong base. And then we can now have a look to a weak base, guys, but everything is the same. We repeat now practically the same idea here. Now, for the weak base, same story. The Ka will be low. The Ka will be low for weak bases there. One example, remember we mentioned that one in previous videos, is ammonia. So if we have NH3, and NH3, which is aqueous solution, is going to dissociate in water. So in this case, because it's a weak base, it's not going to dissociate completely. It's going to dissociate incomplete. So in this case here, what we have is that the arrow will be shifted to the left. That is what happened there. And you will have here form the NH4 plus aqueous solution plus the OH minus in aqueous solution. So if we calculate the Kb for this one, the Kb here is going to be equal to the concentration of NH4 plus multiplied by the concentration of OH minus divided by the concentration of NH3. Alright, what we need to know here, that the Kb here is going to be low because this one is a weak base. Alright guys, and this is it. So now we know the Ka for strong and weak acids, and we know the Kb for strong and weak bases. This is the part of the video, Ka and Kb. The good thing, here is a mistake here, it's a Kb, not Ka. Let's quickly fix it there. Since Kb, we're talking about bases, okay? Every time we speak about bases, it's Kb. So in this case, you can see it's going to be high, and in this one is low, okay? And just to finish this video, we are going to be talking about the autoionization of water. Now, what is the autoionization of water? That is the reaction of water with itself to form H3O plus and OH minus ions there. This is what we call the autoionization of water. So what is going to happen here actually is that water will react with water, and this one will ionize equally. It's going to ionize to form concentration of H3O plus aqueous because it's ions in solution of water or in water, plus OH minus also aqueous. This is what we call the autoionization of water there. Now, this case, we are not going to be called Ka or Kb. We're going to call it Kw, the equilibrium constant for the autoionization of water. And if we calculate this one, remember it's concentration of product divided by the concentration of reactant. We have that this is the concentration of H3 O plus multiplied by the concentration of OH minus. Alright, but in the reactant everything is liquid, so you don't add it there. So this is the Kw for water, in other words the dissociation constant for water, guys. And we know that if the temperature is 25 degrees Celsius, then it was calculated that the Kw was equal to 1,0 times 10 to the minus 14. That is the Kw. You're going to use this constant. It is going to be given to you because using this one, we can calculate either the concentration of H3O plus or the concentration of OH minus there. Now, what we said previously is that you are not, or you will not be able, or you will not be asked to calculate Kb or Ka, but you will have to use the Kw. You won't have to calculate it because it's going to be given, but you will have to use it because you will need these ions later on in further calculation. Guys, this is all for now. We learn about Ka, we learn about Kb, and we learn about Kw. I hope you understand. I hope it helped. If it did so, please subscribe for the channel, thumb up. I'll see you next time. Mr. G here.